Today I'm going to be comparing different variations of microscopy to optimize visuals with the microbe Vibrio fischeri. Vibrio fischeri is a bioluminescent marine bacterium that has evolved with the Hawaiian bobtail squid, seen on the right. Light microscopy is the most common form of microscopy. Bright field, the most generic form of light microscopes, is best with either alive or naturally colored specimens or dead and stained. In the picture here, you can see that live translucent specimen barely shows up, so we won't be able to use bright field to visualize Vibrio fischeri. Instead, we'll take a look at these other microscopes. The only difference in compound microscopes of light field and dark field is the opaque insert shown here that blocks and scatters most of the light, lighting the specimen indirectly and creating a dark background. Both have a resolution maximum of 200 nanometers. Dark field microscopy is depicted in the top left, where Vibrio fischeri cells are illuminated by both an external light source and their own natural luminescent emission. Both of these create greater contrast, allowing us to see the 2D shape, general structure, and natural bioluminescence of Vibrio fischeri. Phase contrast microscopes employ an optical mechanism to translate tiny variations in phase into visual differences in image contrast. As a result, the dynamics of ongoing biological processes can be observed and recorded in high contrast and sharp clarity of minute specimen detail. Disadvantages for Vibrio fischeri, although, are that of a halo can result especially when the organism emits its own light. Here in the photo are human cells. Confocal microscopy reaches a resolution of 180 nanometers laterally and 500 nanometers down into the specimen, creating a wonderful 3D image. Fluorescence can be used well with confocal microscopy to highlight different parts of a cell. On the bottom left, a squid's light organ reveals its folded complexity and dynamic function in symbiosis. If no fluorescence can be used, a color laser can be used as a light source, as seen in the photo to the right, where a green laser channel shows the structurally altered cilia that form in areas of bacterial association. Wide field microscopy is similar and also uses fluorescence. Instead of pinpointing light, the entire focal volume is illuminated, creating a blur from areas out of focus. Wide field fluorescence should be used to get faster, simpler images to check if an organism is alive or simply there. Instead of light microscopy, electron microscopy can be used to get higher resolution and magnification due to electrons' smaller wavelengths than light. TEM, or transmission electron micrograph, is optimal only for 2D imaging of internal structures, nothing external. Unfortunately, the process of preparing the thin slices of cells kills them, but the amount of detail is worth it. On the left, the light organ crypts show the proximity of Vibrio fischeri cells to host microvilli. SEM scanning electron micrograph sweeps electrons over a dead cell surface, sending them bouncing off to give us a 3D and highly detailed image of the surface, but no internal structures. Thank you for watching.